So in this video, we're going to go over quite an interesting concept of how we can tell where we are in a reaction and how we can achieve equilibrium. So I want you to remember and think about how when we talk about equilibrium, we talk about this KEQ value, which is this constant that tells us whether products are favored or reactants are favored. And our KEQ is always our products over reactants. So if we have a high KEQ value, that means we have a lot of product and we don't have a lot of reactants. If our KEQ is small, we say we have a lot of reactants and we don't have a lot of products. And that makes sense because I want you to think, let's say we had 1,000 product and we only had 2 reactant. Now 1,000 divided by 2 will give us 500. That's a very high KEQ. That tells us that our products are favored. The same goes for if reactants are favored. If our reactants are favored, well, if we have 1,000 on the bottom and 2 over here, we're going to have 1 of 500th. Now, that's a really small number. So that kind of gives us a mathematical point of view of how when products are high, KEQ is large, but when reactants are high, KEQ is small. Now, what's interesting about the reaction quotient is that it tells us where we are in our reaction. When we calculate our reaction quotient, we may or may not be at equilibrium, and it tells us where we need to go in order to achieve equilibrium. And that's what makes it so interesting. So let's say we want to calculate our reaction quotient. The reaction quotient is calculated the same way as our KEQ. It's essentially products over reactants. But remember how normally when we calculate our KEQ, we always have to use those ICE tables and we have to use those values at equilibrium in order to calculate our KEQ. In this case, when we calculate our reaction quotient, we do not need to use an ICE table because we do not need to be at equilibrium to determine our reaction quotient. So to find our reaction quotient, ICE tables are not needed because we do not need those equilibrium values. Now, when we calculate our reaction quotient, once again, we go products over reactants and we get some sort of a value. Let's say that our value is really small, okay? So let's say that our Q is really small and our K is bigger. What does that tell us? Well, we need to think about this equation over here. If we have a big KEQ and we have a small Q, and we want that small Q to reach our KEQ, so how are we going to make this Q bigger? Well, in order to make this equation, the product of this equation bigger, we have to increase the number of products that we have. To increase the number of products we have to shift the reaction to the right. Now I hope this makes sense because it can be kind of confusing. I'm going to explain it one more time. So let's say our Q is smaller than our KEQ. How do we get our Q to be bigger? Well, if the equation for Q is the same as KEQ, how are we going to make the Q bigger with this equation? We can make it bigger by making the concentration of product bigger and lowering the concentration of reactants. So that means we push our reaction to the right or we push it towards the products. Now, let's say that our Q is bigger than our KEQ. So we have a large Q and we have a small KEQ. So how do we make this Q smaller? In order to make this Q smaller, we have to make the reactants larger and the products smaller because we want to get a smaller number. In order to get a smaller number, we have to increase our concentration of reactants. To increase the concentration of reactants, we have to push the equilibrium to the left or towards the reactants. And now lastly, when our Q is equal to K, well, we can tell that when our Q is equal to K, well, K is our equilibrium constant, so that means we must be at equilibrium. And this is very interesting because if we're running a chemical reaction and we want to know how to achieve equilibrium, we can simply calculate our reaction quotient and figure out which direction our reaction needs to move in to achieve equilibrium.